Now let's practice how to determine the hybridization of an atom from a given Lewis structure. We're going to first calculate the needed number of hybrid orbitals to be able to hold the sigma bonds and lone pairs on that atom. In some cases though, the lone pairs may not be shown on the Lewis structure. For example, looking at our oxygen, we are given that it has 2 bonds but no lone pairs. However, in order to obey the octet rule, oxygen needs some electron pairs. Octet rule says that oxygen should have 8 electrons around it, or 4 pairs. It currently has only 2 pairs. That means oxygen must have 2 lone pairs on it. The double bond also consists of a sigma and a pi bond. So on oxygen we have 1 sigma bond and 2 lone pairs, a total of 3 electron domains. Therefore, oxygen requires 3 hybrid orbitals. To make 3 hybrid orbitals, you need 3 atomic orbitals, which you need to take 1 s and 2 p orbitals to make. Therefore, the hybridization of oxygen is sp2. If you look at the carbon, it is already making 1, 2, 3, 4 bonds, so octet rule is satisfied. And out of those 4 bonds, 1, 2, 3 are sigma bonds and 1 is a pi bond. So it has 3 sigma bonds but no lone pairs, total of 3 domains needed, so it needs 3 hybrid orbitals. Therefore, the hybridization of this carbon is also sp2. 1 s and 2 parts p make 3 hybrid orbitals. This carbon over here is making 4 bonds, has no lone pairs on it, doesn't need lone pairs because it's already making 4 bonds. Out of those 4 bonds, only 2 are sigma bonds, 2 are pi bonds, so it needs 2 hybrid orbitals. Therefore, hybridization is sp. When it comes to nitrogen, it is shown to make 3 bonds. To satisfy the octet rule, it needs 1 lone pair of electrons. Overall, nitrogen has 1 sigma bond, 1 lone pair, and 2 pi bonds. Therefore, 1 sigma, 1 lone pair makes a requirement for 2 hybrid orbitals, which makes nitrogen sp hybridized as well. For organic compounds, skeletal structures are commonly used to represent their structures. In skeletal structures, carbon atoms are mostly not shown, they are implied, to be at the corners of each line or at the ends of the lines. Each line represents a bond. A double line represents a double bond. Looking at such a structure, you need to be able to determine the number of sigma bonds and lone pairs on each atom. The starting point is the octet rule and the number of bonds each atom will make. Looking at this atom indicated by A, there's a carbon atom in this corner. This carbon atom is making 1, 2, 3 bonds. Carbon normally doesn't have lone pairs. So how can this carbon atom have 4 bonds or 4 electron domains around it? It's by having a hydrogen attached to it. This carbon carries a hydrogen. So if you count the number of sigma bonds on it, there will be 1 sigma bond here, 1 sigma bond here, 1 sigma bond here. This other bond is a pi bond. Therefore, there are 3 sigma bonds, making this carbon needing 3 hybrid orbitals to make these 3 sigma bonds. So therefore, this carbon is sp2 hybridized. Moving on to carbon labeled as B. It's shown to make only 2 bonds. It needs 2 more bonds. Well, those 2 bonds are to the implied hydrogen atoms. They're not shown, but you can add it there yourself. There's a hydrogen atom and there's a second hydrogen atom, which makes this carbon have 4 bonds. This carbon is now, you can tell it's making 4 sigma bonds. Because it has 4 sigma bonds, it needs 4 hybrid orbitals, making the hybridization sp3. Looking at the nitrogen labeled C, it's shown to make a sigma bond here, a sigma bond to the hydrogen, and a sigma bond to that carbon. But remember, nitrogen in its Lewis symbol has 1, 2, 3, 4, 5 electrons. There is a lone pair. So nitrogen is expected to have a lone pair, and this nitrogen also has a lone pair. So this nitrogen has a total of 3 sigma bonds and 1 lone pair. It needs 4 hybrid orbitals. Therefore, its hybridization is sp3. Now pause and determine the hybridization, electron domain geometry, and molecular geometry in the indicated atoms below.